Okay. Now, today I will discuss about sampling of analog signals. Okay. Then I will go to the next part where I will discuss about the different representation of discrete time signals and systems. Okay.
So you are not audible.
Hello. Am I audible to
Yes,
you?
sir.
Yes, sir.
Yes, sir. Now you are audible.
Yes,
Whatever
sir.
I,
Yes, sir. Yes, sir.
whatever I told just now, you
It
listened.
wasn't audible, sir. No, sir.
No, sir. You're not audible.
So I will means stop your access if you do that. Okay. And I will not give any access to record the meeting also for your purpose. Please don't do this. Now, suppose this is a signal. I am drawing the signal graph of a signal, arbitrary graph of a signal. And the horizontal axis is representing the time variable. And the signal is a function of time. And the signal amplitude is represented by xt. Now, from this graph, we see that the signal is continuous function of time because for each and every time, at each and every time instance, the signal is defined. Now, if I want to sample this signal, one particular electronic device is available to us. This is called sample and hold circuit. Sampler, sometimes it is called sampler. It is nothing but sample and hold circuit. Using this circuit, I can sample an analog signal or analog continuous time signal. Now, I will not draw the internal diagram of the circuit. Just I will show the block diagram. Okay, and nothing else. I want to show the mathematical details of the signals. Suppose this is a signal. Now you can use this sampler circuit. Suppose this is your sampler circuit. Okay. And this input is xt. You can use, okay, I am writing xt, no problem. Okay. And here one switch is there. Okay. The switch at every ts second, the switch will be closed and then again it will open. Okay. Then at the output, you will get some sample signal xst. This will be the sample signal. And this device I have shown here in block diagram form. This is called actually sampler. Okay. And Here the sampling frequency Fs is denoted by Fs, and it is the reciprocal of the time, the sampling time interval Ts. Okay. Now I will show how this particular signal is sampled. Suppose here at t is equal to 0, you are taking one sample value. Okay. At t is equal to 0, you are taking one sample value. And then at t is equal to here, at this point, after a distance.
Are you writing something on the screen, sir?
Huh?
Sir, are you writing something on the screen, sir? Because it's
Yeah, I have already shared it, and I asked that I am sharing, and some people told that okay, they are seeing this, they are able to see this.
It's visible, sir.
Huh?
So it's visible, sir. So
Yes,
it's
sir.
visible,
Yes,
sir,
sir.
but it's lagging a lot, sir. So like
It
you're
is
writing something,
visible
so
or
it's
not?
coming a little later.
Huh?
Sir, actually it's lagging, sir. It's like you're writing something, sir, but it's coming a few minutes later, sir. That's the thing, sir.
But this may be due to the speed of the the speed of the internet. So if it is due to speed of the internet, then I have nothing to do. Okay.
Okay, sir.
No, sir.
So it may be due to this problem. Okay. Now what I can do? Okay. Just I am stop sharing. Okay, and then again, let me share this.
Yes, sir.
But here, where is the? No, I have to dismiss this. This MS team is not okay for teaching. That's why I did not use in the last semester. Okay, I did not use this. Because it is not showing. Yeah. Now let us see. I have shared this. Is it visible to you? Huh?
Yes, sir.
Okay. Now here Fs is equal to 1 by Ts. And what is Ts, you see? Ts is the sampling time interval. Means suppose this is your first sample, this red one, and the second red sample is the next sample, and third sample is this one, fourth sample is this one, fifth sample is this one, sixth is this one. So in this way, you can sample the whole signal. So these are the sample values. And what about this Ts? Ts is the distance between two successive samples. For example, this is one sample and this is another sample. So the distance between these two samples is Ts. Similarly, you can take two arbitrary successive samples. For example, here, this is one sample, this is another sample. And the distance between these two samples is equal to again Ts. And therefore, the Ts is called sampling period. Sampling period. Okay. And the reciprocal of Ts is called sampling frequency. This one. This is your Fs. Fs is called the sampling frequency. It is sampling frequency. Sampling frequency, which is reciprocal of the time sampling period. Now, suppose this is your nth sample. Okay. This is your nth sample. If you think that this is the first sample and second, third, fourth, sixth, seventh, like this is seventh sample. The seventh sample will be obviously X6. Okay. Now I want to write here in this form, then it will be clear. First, I am removing this. Okay. So if this is 0, this first sample is situated here at the origin. Therefore, this point will be 0 and this point will be TS and this point will be 2TS. This point will be 3TS. So it will means move in this way towards right side of the axis, time axis. And suppose this is your NTS, this sample. So this sample value, if this time instant is NTS, N is integer and TS is the sampling period. And this sample value can be represented by X NTS because actually the signal is XT. Therefore, at T is equal to NTS, you are computing the value of the signal. Therefore, in place of T, you have to write NTS, and this NTS is the sample value. NTS is the sample value of this. Okay. So sometimes it is written in this form XT provided that T is equal to NTS. So this sample value NTS, sometimes it is written in this form also XN only, just by removing this TS, because the TS time period is a constant term. So it is not required to give the to put within the argument of this function X. We can remove this TS from here as it is a constant term, and N is the variable, integer variable. Therefore, in the argument of X, if you write N, then it will be sufficient. But you should mention what is the time sampling time period. You should mention separately. Just like this, suppose this is one signal XT. This is sampled at every 1 millisecond. Every 1 millisecond, and then 10th sample will be X10. Sorry, 10th sample will be written as X10. Means N is equal to 10. Okay. N is equal to 10. For N is equal to 10, the sample value will be X10. So this is the sampling. In this way, you can generate the sequence of samples from the analog signals. Okay, this signal XT may be a voltage signal, it may be a current signal. We do not bother about that. However, whatever may be the signal, ultimately the argument will give the amplitude of the signal. If the signal is voltage, then the amplitude will be represented by voltage, volt. And if the signal is current, then the amplitude will be represented by ampere unit. Okay, so this is our sampling. Now, after sampling the signal, what you see that each and every sample value, it has a certain value. For example, if you consider this nth sample, suppose nth sample, the nth sample will be represented by xn. Okay, suppose here 1, 2, 3, 4. Suppose this is your fourth sample, then fourth sample is equal to will be represented by here. Actually, it's not nth sample. If I think about the number of samples, it will be n plus 1th sample, because you have started from n is equal to 0. Okay. So then fourth sample means actually x3. 1, 2, 3, 4. This is fourth sample, but here n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. That means the argument will be 3. Okay, so x3, suppose this x3, this sample has a certain value, certain height. So if you measure this height, it will give the value of the signal at n is equal to 3. For example, this value is 1.5 volt. Suppose this is a voltage signal and it is given in volt. If nothing is given means actually if the nature of the signal, whether this is a pressure signal or voltage signal or current signal, this thing is not given, only the value is given, then you will write, okay, you will write only the value here, 1.5. However, whatever may be the case, the value of the signal is 1.5 and this 1.5 is a real number. It is not an integer, it is a real number. Okay, since this number is a real number, then you see, if you want to represent this sample value by using binary digits, because ultimately what is our aim? Our aim is to process the sample values by using a digital device. And you know, a digital device can handle only binary digits, 0 and 1. Therefore, whenever I want to process some signal which has some decimal value, we have to convert that decimal value into binary. We have to represent the decimal value into binary representation. So if you want to convert this 1.5, this particular number into binary number, then how many bits are required? You can calculate. You can convert this number into binary number and you can calculate how many bits are required for representing this 1.5 into binary form. Similarly, if one signal is like this, suppose 1.73. Okay, then how many bits are required? You can, okay, again you can calculate. Is it possible to calculate always? Since this is a real number, sometimes it may happen that since this is a real number and fractional number, you see, so integer part is easy. You can represent the integer part easily, but fractional part it will be difficult. It is not always possible to represent the fractional part of the number by using a finite number of bits. But your device on which you will process the signal, that is a finite state device. It can handle only finite number of bits. It is not possible to handle infinite number of bits by using computer or any kind of digital processor having finite memory size. Therefore, what you have to do, you have to, convert. You have to quantize this signal. Means quantize means you have to convert this analog signal or analog sample value, analog discrete sample value to a digital number. And when you want to do this, then obviously you have to represent the sample values in a finite number of states, finite number of levels. Okay, so I think you have studied ADC conversion technique. By using ADC conversion technique, any analog signal can be converted into digital number. Successive approximation type of ADC, I think you know. Okay, so it is this successive approximation ADC is used for converting the analog signal into digital signal. Obviously, in that conversion, some error is there that is called quantization error, because quantization is done there. And quantization means actually, suppose a signal value is, for example, 5.0. Just I am giving an example like this, 5.01, and then just I will quantize this as 5. Then it is possible to represent this number 5 by using finite number of bits. This is one example I am giving. Since this 5.01 is represented, it is quantized by a number 5, therefore some error is there. That is called quantization error, and this quantization error is this 5.01 minus 5. What is the actual value minus what is the quantized value? This difference is called the quantization error. Therefore, in digital signal processing system or digital signal representation system, whenever you want to convert an analog signal into digital signal, therefore in that case there is some error always present. Okay, some error is always present in that case, and this error is called quantization error, and obviously this will hamper the performance of the system if the quantization error is very large. Okay, I don't want to go far behind this conception in this chapter. Later, if time permits, then I will discuss a little bit more on this particular quantization technique. Okay, so what I want to say that this is simple sampling process of an analog signal. Next, I want to discuss about the signal, discrete time signal representation, discrete time signals and systems. So the next topic is, I'm writing here, discrete time signals. And systems. Okay. Then I will go for this processing. I think all of you know Fourier series expansion of signals and Fourier transformation. You know, you have studied in mathematics, Laplace transformation, Fourier transformation. Have you studied in mathematics subject?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. Now, I will use this Fourier transformation technique, Fourier transformation technique or Fourier series technique later for analyzing the signals. Before that, I want to represent different types of signals in different format. So signal representation, discrete time signal representation. So let us write this discrete time signal representation. Discrete time signal representation. Okay. The first one is functional representation. How can you represent discrete time signal by using functional representation technique? By following this functional representation in this way. Suppose x n is equal to, for example, 1 for n is equal to 1, 3. Suppose this is equal to 4 for n is equal to, for example, 2. And suppose this is equal to 0 for, you write otherwise. Otherwise. Okay. So this is functional representation. No? Now, if I tell you to draw this particular function, it is possible to draw this. No? It is possible to draw. For example, this horizontal axis is representing n, and this vertical axis is representing xn. N is integer. So here n is equal to 0 at this point. I am just marking the points here by using red dots. red colored dots. These are the different points. Okay. Now this is the origin, and here n is equal to 0. So n is equal to 0 here. And here for next point is n is equal to 1. You can write n is equal to 1. Then for this n is equal to 2, n is equal to 3, n is equal to 4, so and so. And the left hand side n is equal to -1, n is equal to -2, n is equal to -3, so and so. Now for this signal xn, for n is equal to 1 and 3, so 1 and 3, the value is 1. So you can write here 1, suppose this height is 1, and here 1, n equal to 1, 2, 3. So 1 and 3, this values are 1. For n is equal to 2, the value is 4. Here n is equal to 2, so value is 4. So you can. So suppose this is the sample value at n is equal to 2. And 0 otherwise. Otherwise 0 means other values, for other values are 0. So I am not drawing the samples for other points. So this is a graphical representation of this function, this particular function, discrete time function xn. And this representation is called functional representation. Okay. Now, next is, tabular representation. All of you know this. What is tabular representation?
Sir, the functional representation is xn equal to 140. That part.
Xn is equal to 1 for n is equal to 1, 3. I wrote like this, na?
Yes, sir. Is that the functional representation, sir?
Not this one. It is 4 for a group of values are there. For n is equal to 2.
Yes.
0 otherwise. So this whole thing is functional representation. This whole thing. Okay.
Okay, sir.
And then next is a tabular representation. And in this representation, what we do, just you write horizontal line, then you make this kind of table. Okay. Suppose this is your n and this is your xn. Okay. Okay. This xn value. For n is equal to, suppose I am putting dot sign here, means for negative values are 0, I want to say. -2 it is 0, -1 it is 0. Suppose for 0 it is 0. For n is equal to 2, some value is there. It is 1. It will be 1. For n is equal to 1, suppose some value is there, 1. For n is equal to, suppose 2, xn is equal to 4. For n is equal to 3, xn is equal to 1. Again, and then for n is equal to 4, xn is equal to 0, again it is equal to 5, xn is equal to 0, and again it will continue like this. This is a tabular representation. You see the same signal which I just represented in functional form, functional representation form. The same signal is represented in tabular form in this way. Now here see, for n is equal to 1 and 3, the values are 1. For n is equal to 2, the value is 4. And for other values of n, you see the values of xn is equal to 0. For other values of n. So if you plot the n versus xn graph, so the representation will be same in graphical form. Okay, so this is tabular representation. Now, then I want to write the sequence form, sequence representation. Okay. Now for sequence representation, the signal xn, any signal xn will be represented by, it will start from this second bracket, using the second bracket first. Okay. Then you can give dotted sign, then 0, then suppose 0, then 1, comma 4, comma 1, comma 0, comma 0, comma, and dot dot. This dot dot means actually for other values of n, this 0 will continue. Here dot 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 0 means in this side 0 0, in left side the 0 is continuing here, and this side 0 is continuing. Okay. Now here what I will do, I will put some arrow sign to represent, to identify or to indicate the position of the origin. Where is n is equal to 0? If I don't put this kind of arrow sign, it is not possible for you to say what is the value of xn at n is equal to 0. But if I point here using some arrow sign like this, then this arrow sign indicates that this is the value of the signal at n is equal to 0. So this value 0 is the value of the signal at n is equal to 0. And this value is the value of the signal for n is equal to 1. This value is the value of the signal for n is equal to 2. This value is the value of the signal for n is equal to 3. This value is the value of the signal for n is equal to 4, so and so. Similarly, in the left hand side, this is the value of the signal for n is equal to -1. Then here if some signal is there, for example, here comma, and then some signal is there, that means this signal is the value of the signal for n is equal to -2. This is for n is equal to -2. Just I am writing here. This is for n is equal to -2, so and so. On the left hand side, you will proceed in this way. So this arrow sign is very important sign, which should be given when we will try to represent any discrete time signal in sequence representation form, because it will indicate the value of the n, value of the dependent variable. And the arrow sign here, where the arrow sign is given, that value will be represented by the value of the signal where n is equal to 0. So it is the value at the origin. It is the value of the signal at origin. Okay. So this is sequence representation of the signal. Now, next I want to discuss some elementary signals, some elementary discrete time signals.
Sir, we have classes from 4:30 p.m.
Okay. It is 2:29. Okay. Then next class I will discuss this. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.